Imagine you have a table with a hole in the middle of it and a rope packed around that hole and a part of it hanging inside the hole. If this length here is x and this part is falling down, and the rope is packed around around that hole in a way that with a really small tension, any part of it would fall inside the hole, so that different parts of the rope don't move on the table, they only fall into the hole. We're trying to find out x, the length of the part of the rope which is hanging and falling down, as a function of time. With this initial conditions, x when t is 0, and x dot, the speed of the falling rope, is also 0 when t is 0. So we have Newton's second law, F equals dp over dt. F is lambda times x times g, basically mg. This is equal to derivative with respect to time of the momentum of this piece of rope, which is lambda times x, the mass of this part of the rope, times x dot, the speed of that part of the rope. The lambdas cancel out from both sides, and we would get x times g is equal to d over dt of x times x dot. Okay, now we have this differential equation, and we're trying to solve it. Okay, here's where the magic happens. I'm going to write d over dt, the derivative with respect to time, as dx over dt times d over dx, the chain rule. So from that, we would have x times g is equal to x dot dx over dt times d over dx of x times x dot. Then I'm going to multiply both sides by a factor of dx. X times g times dx is equal to x dot times d of x times x dot. And then I'm going to multiply both sides by x. So what we would get would be x squared times g times dx is equal to x times x dot times d of x times x dot. So now if I integrate both sides of this equation, what I would get would be x cubed over 3 times g is equal to x times x dot squared over 2 with an integration constant which is 0 because of this initial conditions here. So the x squared terms cancel out from both sides, and I would get that x times g over 3 is equal to x dot squared over 2. And from that, I can write x dot is equal to square root of 2 times x times g over 3. And from that, I can write that dx over, I can write x dot as dx over dt and then swap the places of dx, dt, and this is square root here, over 2 times x times g over 3 is equal to dt. And again, if I integrate both sides, I would get t is equal to, we know that the integral of 1 over square root of x is equal to 2 times the square root of x plus some constant. And from that I can write 1 over square root of 2 times g over 3 times 2 times the square root of x. And if I simplify, I would get t is equal to the square root of 2 of 6 times x over g. And from that, I can easily show that x is equal to g over 6 times t squared. And we can write this as 1/2 of g third times t squared, which is a constant acceleration motion, and that's the solution to this problem. Yeah. The first time I solved this problem, when I got to this place, I was like, this couldn't be the answer to this differential equation here. This doesn't look like it has such an simple answer. But the only reason that we get an answer this simple is these two initial conditions we have here. If the initial conditions were different a little bit, such that when x dot is 0, x wasn't 0 when x dot was 0, the answer wouldn't have been this simple, because we'd have some integration constants here, and everything would have been messed up from this place to down. Yeah, that's it. I hope you guys enjoyed it, and see you later.